Good morning. Myself, Dr. G. Venkat Subbareddy, Associate Professor of EEE Department, G. Polarity Engineering College. Today, I will going to discuss about my subject is Power System 2. In this power system, there are 5 units. Among these 5 units, the first unit will be understand the per unit quantities, symmetrical component theory and short circuit analysis like shunt and series fault calculations. The second and third unit will be stability analysis. In this stability analysis, we discuss about steady state stability, transient stability and dynamic stability. And the third unit will be according to transient stability. In case of transient stability, we discuss about the solution of the swing equation, derivation of swing equation, the solution of swing equation using point by point method and equal area criterion method and applications of equal area criteria. By using equal area criterion, how to determine the stability of the system. Finally, we discuss about methods of improving of transient stability. The last 2 units are load flow studies, that is nothing but power flow studies, how the power is transferred to the buses to the system. That is nothing but in case of load flow studies, there are 2 units. Fourth unit will be Gauss-Seidel solution of load flow solution by using Gauss-Seidel method and classification of load flow studies, and final unit will be the solution of load flow studies using Newton-Raphson method, fast decoupled solution. Today we discuss about the first unit, that is nothing but understanding of per unit quantities, symmetrical component theory and short circuit analysis and shunt faults. Among the subject within power system 2, the course outcomes are: the first one, understand the per unit quantities, symmetrical component theory, short circuit analysis and shunt fault calculation. At the end of the first unit, student will be outcome of the first unit. In case of completion of second unit, student can able to understanding the steady state, transient and dynamic stability, that is nothing but elementary concept of steady state stability limits. The third one is after completion of third unit, student will able to understand the swing equation and the solution of and application of equal area criterion to determine the stability of the system, and the last one is methods of improving of transient stability. At the end of the fourth unit, to understand the need of power flow studies and obtain the load flow solution using Gauss-Seidel method. The last one is student will able to understand the Newton-Raphson and FDC method for load flow studies. The syllabus for first unit, short circuit analysis 1. The first unit can be divided into 3 parts. The first part will be short circuit analysis 1 and short circuit analysis 2. The third one is unsymmetrical fault calculations. In case of short circuit analysis 1, what is the per unit system? What is the equivalent of per unit system can be represented into equivalent impedance diagram and reactance diagram, and numerical problems for the solution of single line diagram after drawing the impedance diagram. Then how to calculate the short circuit current and short circuit MVA calculations and fault level. And one more important topic is applications of series reactors, that is to limit the short circuit current, then apply that is using for reactors. The second topic means the short circuit analysis 2. In this topic, we discuss about symmetrical component theory, that is nothing but any phase component can be converted into symmetrical components, and symmetrical components is also transformed into phase components. And that is any phase component can be represented as the sum of the positive, negative and zero sequence component, that is nothing but a positive, negative and zero sequence component of voltages and currents and impedances. And the third topic will be in the first unit, unsymmetrical fault calculations. Unsymmetrical fault calculations is nothing but the positive, negative and zero sequence network, how to draw the positive, negative and zero sequence network, and what are the sequence network diagrams for unsymmetrical faults like LG, LL and LG fault with and without fault impedance. One more is nothing but triple L fault, that is nothing but a symmetrical fault. In case of single line diagram, the single line diagram is representation of the essentials of the system in most simplified form. The entire power system can be represented in one diagram, that is nothing but a single line diagram. Single line diagram is essentially consists of generator unit, transmission effects and loads, that is nothing but industrial, commercial and residential loads. That is nothing but entire power system can be represented one diagram, that is nothing but a single line diagram. That is nothing but main components of the power plants are generator plant, transmission lines and distribution lines. And loads are industrial, commercial and residential loads. Now all these loads in the form of the phase quantities. This is nothing but, for example, one single line diagram. In case of in this single line diagram, the entire system can be represented one diagram, that is nothing but a initially generator. After generator, then will be a transformer. After generating voltage of 11 kV, that can be step up to the 33 kV, whatever may be, by using the step up transformer nearer to the generator. After that, transmission lines and one more transformer, that is nothing but a step down transformer, that is nearer to the loads or motors. That is entire, all these components can be represented in one diagram, that is nothing but a single line diagram. In this example, one generator unit, the second one is nothing but a transformer, T1 is nothing but a transformer, that is nothing but a step up transformer. The another one is a transmission line, J60 ohms is nothing but a transmission line. The another T2 is nothing but a transformer T2, that is nothing but a step up transformer. The transformer nearer to the modes or loads, so that is considered as a step down transformer. Here one motor. Then in case of while representing the single line diagram, all these components can be represented in the bottom of the diagram. The ratings of all the components can be represented at the bottom of the diagram. That is nothing but a generator. The generator rating is 40 MVA, 11 kV and subtransient reactance is 20%. And motor ratings are 30 MVA, 11 kV and subtransient reactance is 30%. And transformer T1, 40 MVA, 11 by 20. This is nothing but a step up transformer. 11 kV transform into 220 kV and subtransient reactance is 15%. And another step down transformer. The T2 is nothing but step down transformer. The ratings are 40 MVA, 220 kV by 11 kV and subtransient reactance is 15%. And the ratings of the line impedance is represented as a 60 ohms. That means generator, transformer, transmission line, another transformer, motors, any components, all are represented in one diagram, that is nothing but a single line diagram. The representation of single line diagram is entire diagram is represented one diagram and the ratings of all these components are measured at the bottom of the diagram. These rectangular boxes are represented as a circuit breakers. A circuit breaker is a device which opens automatically or manually when the fault is occurs. To simplify this single line diagram, for short circuit calculation, the single line diagram can be represented equivalent impedance diagram. In case of impedance, this is a symbols of rotating machine, 2-winding transformer and 3-winding transformer, fuses, current transformer and potential transformer. These are symbols are used for single line diagrams. Then oil circuit breakers and airbag circuit breakers, delta connection, star connection with neutral grounded. That is nothing but impedance diagram. While drawing the single line diagram, in this single line diagram, the generator is represented as a constant voltage source behind the proper impedance, and the transformer is represented as its equivalent circuit, and transmission line is represented as a nominal pi method, equivalent nominal pi method. Another transformer is represented as a equivalent circuit, and motors are represented as a inductance, resistance, inductance are connected in series. That is nothing but representation of single line diagram to impedance diagram. In case of impedance, this is the impedance diagram on a single phase basis under balanced operating condition can be drawn in one diagram. First, single line diagram can be transformed impedance diagram by drawing its assumptions. Single phase transformer equivalent as shown in ideal transformer, the transformer impedance is indicated in appropriate side. Transformer is replaced by its equivalent circuit. Generators are represented by a voltage source in series with resistance and inductive impedance. That is nothing but a generator is represented a constant voltage source behind the proper impedance. Transmission line is represented as a nominal pi circuit, and loads are represented by resistance and inductance in series. Neutral grounding impedances are neglected while drawing the impedance diagram. There is nothing but equivalent single line diagram, equivalent impedance diagram for the above example. That is nothing but a single line diagram. Then generator can be represented as a constant voltage source behind the proper impedance, constant voltage of proper impedance, and the transformer T1 is represented as equivalent circuit. That is nothing but R0 and X0 is a parallel components. R01, X01, R02, X02 is nothing but a series components. In the transmission line, J60 ohms are represented as a nominal pi circuit. That is but impedance and y by 2 y by 2, that is not the equivalent transmission line is represented as a nominal pi circuit and transformer T2 as represented as equivalent circuit. In the last element is motor that can be represented as a impedance. Resistance is connected in series with reactance. Next, by by drawing the reactance diagram by simplification, and the impedance diagram is converted into reactance diagram by making some assumptions. The resistance of the generator is neglected. In case of transformer, magnetizing components and series resistance are neglected, and the transmission line, shunt admittances and series resistance is also neglected. In case motor, the resistance is neglected. The simplified reactance diagram of the given single line diagram is represented as reactance. This is useful for calculation of short circuit kVA and short circuit current by drawing the single line. While calculating the short circuit current and short circuit MVA for given single line diagram can be replaced by a reactance diagram by making some assumptions. This is nothing but equivalent reactance diagram of the given single line diagram. This is the online single line diagram. The example is another example that can be converted into impedance diagram, and impedance diagram is also by simplification of reactance diagram. This is another example for drawing the reactance diagram. This is a one more single line diagram by making some assumption while drawing the impedance diagram, finally drawing the reactance diagram. Next, that is a first important topic is what is the impedance diagram, what is the single line diagram, how to representation of the single line diagram, how the single line diagram can be mixed an impedance diagram, finally impedance diagram, how to convert the reactance diagram. One more important topic is per unit system. The per unit system is most important in power system analysis. That is, what is the per unit system? Per unit value of any quantity is defined that the ratio of actual value of the quantity to the base value of quantity in decimal. That is the ratio of actual quantity divided by base quantity. Per unit system is nothing but a dimensionless parameter. That is a numerator and denominator which have a same units. That is nothing but a per unit system. Sometimes it is more convenient to represent the value of current, voltage and impedance and power in per unit values rather than amperes, voltage, ohms and kilowatt, because it is a unitless. This is the many advantages by using per unit system. It is unitless parameters. The ratio will be same dimension. The per unit value is the ratio of the actual value to the base or reference value. Actual divided by base is nothing but a per unit system. Sometimes per unit quantities ID is mentioned as per the percentage quantity. Percentage value is equal to per unit value into 100. That is nothing but some example. A per unit actual any quantity, the per unit is represented as actual value divided by base value. A per unit A actual divided by A base, I per unit I actual divided by I base, V per unit V actual divided by V base, like this. If any of three quantities, current, voltage, impedance, and remaining two quantities is fixed automatically. In case of per unit system, any two quantities have been referenced, the other quantities automatically base or reference value in relation between other two. Advantages of per unit system. The major advantages of per unit system, the calculations are making very simple. The second one is nothing but it is less chances of making mistake by using the per unit systems, like the either calculation of phase quantities or line quantities. Another most important advantage is per unit impedance of the transformer is same whether referred to the primary side as well as to the referred to the secondary side. This is a most advantage by using the per unit system. Ordinary parameters may vary with the variation of physical size, terminal voltage and power rating, etc., while the per unit parameters are independent of these quantities over a wide range of same types of operands. In other words, per unit impedance values is for approximate like rating within the narrow range. It provides more meaningful information. By using the per unit system. The chance of confusion between the line and phase voltage in three-phase balance system is reduced. This is another advantage by using per unit system. A per unit phase quantities has the same numerical value as corresponding the unit line quantity regardless of three-phase connection whether is star or delta. The impedance impedances of the machines are specified by the manufacturer in terms of per unit values. The per unit impedance referred to either side of the single phase transformer is same. That is a fifth point is most important. The per unit impedance referred either the side of the single phase transformer, that is nothing but the per unit impedance of the transformer is same whether referred to the primary side as well as referred to the secondary side. The per unit impedance referred either side of the three phase transformer is same regardless of the connection, whether this is a delta delta or star star or delta star. The competition effort out of the power system is very much reduced with these of use of per unit quantities. Usually the per unit quantities being of order of unit or less can be easily handled with the digital computers. Manual calculations is also simplified. Per unit quantities simply theoretically reduction and give more general information. In electrical engineering, three basic quantities are voltage, current, impedance. Among these three quantities, any two taken as a reference, the third one is automatically base or reference in relation between other two. Then basic quantity, for example, in basic quantities of electrical engineering, voltage, current and impedance are basic quantities. Then voltage, current are basic quantities of the system. Then impedance is automatically base quantities in relation between the voltage and current. Z is equal to V by I. How to selection of base? The ratings, majority of the equipment in a power system is normally measured in terms of operating voltage and kVA. Majority of equipment in a power systems are normally measured in terms of operating voltage and kVA rating. For that reason, these two are selected as a base quantities. That is very useful and convenient to select these two quantities as a base quantities. The ratings of the equipment in a power system are normally given in terms of operating voltage and capacity in kVA. Therefore, it is convenient and useful to select the voltage and kVA ratings as a base quantities. The base values of a system are selected in such way that the per unit voltages and current in a system is approximately unity. That is a selection of base. Current and voltage are selected as a 1.0 per unit quantities, and kVA ratings are selected in such way that the sum of the ratings of all the equipment or the largest unit of any equipment, any arbitrary value. Then I already discussed that majority of the equipment in power system is normally measured in terms of operating voltage and kVA rating. For that reason, these two are selected as a base quantities. That is nothing but VB is nothing but a base voltage and kVA is nothing but a base kilovolt ampere. These are selected as a base quantities. Then per unit voltage, by the definition of per unit system, the voltage V per unit is equal to V actual divided by V base. Base current is in relation between kVA and voltage, kVAB divided by VB into 100. By the definition of current, per unit current is equal to actual value current divided by base value of current. Actual value base current is equal to kVAB divided by V into 1000. Then actual current into VB into kVA into 1000. Then finally base impedance is equal to base voltage divided by base current VB divided by kVAB into 100. Finally, the per unit impedance is equal to, by the definition, actual value of impedance divided by base impedance. Then finally, you get per unit impedance Z into MVA divided by VB whole square. This is a very important relation. Z per unit is equal to Z into MVA divided by KV whole square. That is nothing but per unit impedance of the impedance is directly proportional to rating of the equipment and inversely proportional to square of the operating voltage. The change of base. How to change of base? If the individual quantities, that is nothing but already existing quantities, Z per unit value, kVA nu and V nu, and common base quantities, that is nothing but selected base quantities are Z per unit nu, kVA nu and V nu. Then by using the relation Z per unit nu is equal to Z per unit volt, kVA nu divided by kVA volt, V volt divided by V nu whole square. That is a very important relation in case of power system analysis. The change of base. Old values is already existence of components, new values are selected base quantities, then calculate of Z per unit nu is equal to Z per unit volt into kVA nu divided by kVA volt, V volt divided by V nu whole square. This is a very important relation in power system analysis. Next, one more definition. Z per unit primary side is equal to Z per unit secondary side. That is nothing but a transformer. In case of a transformer, the per unit impedance of the equipment with the same component will be same. The per unit impedance of the equipment corresponding its own rating is defined as actual value divided by base value. Actual value is equal to Z actual, base is equal to V by I, Z into I divided by V, that is equal to per unit value, Z into I divided by V. That is nothing but the definition of per unit impedance of the equipment corresponding its own rating. In case of transformer, already told that the per unit impedance of the transformer is same whether referred to the primary side as well as secondary side. That is nothing but per unit of the transformer is same whether referred to the primary or secondary side. That can be derived. Let the impedance of the transformer is primary side is ZP and secondary side is ZS. By transform the secondary impedance, it transform in the primary impedance. The equivalent primary impedance referred to the secondary side, ZP is equal to ZS divided by K square. K is nothing but Vs by Vb. Z into 1 by K square, Vp by Vs whole square. Then Vp and Vp is the primary and secondary side voltages of the transformer. Then definition of the per unit, the per unit impedance of the transformer corresponding its own rating, Zp into Ip divided by Vp. Then derive that Zp into Ip. Ip to substitute Zp value in the above equation. Then finally you get Z per unit primary side is equal to Zs per unit secondary side. Then this is a great advantage in per unit calculation. That is nothing but the per unit impedance of the transformer is same whether referred to the primary side as well as the secondary side. How to selection of base quantities? The base voltage and base current are selected as 1.0 per unit, but base kVA is selected in such a way that there are three methods. One is nothing but sum of the ratings of the various components of equipment. The second is equal to the capacity of largest element or any arbitrary like 100 MVA or 1000 MVA or 10 MVA. That base kVA is selected in such a way that this is a three method. We can select any one of the method for selection of base quantities. These are some important formulas in case of per unit system. Z per unit is equal to Z MVA into VB, Z into MVA divided by V square. That is a one important relation. The per unit impedance is referred to the corresponding its own rating is equal to Zi into V. The change of bed, Z per unit nu is equal to Z per unit volt, kVA nu divided by kVA volt, V volt divided by V nu whole square. That is one more important. The percentage reactance. This is a formula by using Ix by V into 100. The change of percentage drop divided by total voltage, that is nothing but percentage reactance. One more important relation, the percentage reactance at base kVA is equal to base kVA divided by rated kVA into percentage of reactance at rated kVA. Then to calculate the short circuit calculations, one is a short circuit current. The short circuit kVA is equal to base kVA into 100 divided by total percentage reactance. Short circuit current is equal to full load current into 100 divided by the total percentage of reactance. The percentage of X is nothing but total percentage reactance that can be calculated from the neutral to the fault point. Generator neutral to the fault point. Percentage of X is nothing but the total percentage of reactance that can be calculated from generator neutral to the fault point. The one more formulas will be the percentage X is equal to percentage reaction kVA into X divided by 10 into kVA square. That is one more formula. X is a reactance in Y. Even suppose X is measured in terms of reactance, then by using this formula, percentage of X is equal to kVA divided by into X divided by 10 into kVA square. Then one more important formula, percentage reactance base kVA is equal to base kVA divided by rated kVA into percentage reactance or rated kVA. Short circuit current is equal to I into 100 divided by percentage reactance. These are the formulas for. One more important is series reactors. The series reactors, to limit the short circuit current, to remove the short circuit per particular values, we go for reactors. The reactors are classified into three types. One is nothing but a generator reactors, another one is a feeder reactors, the third one is a busbar reactor. In case of generators, when the reactor is connected in series with each generator, that is nothing but a generator reactors. A reactor is connected in each feeder, that is nothing but a feeder reactance, and reactor is connected in series with the busbar, that is nothing but a busbar reactor. Busbars are connected into two types. One is nothing but ring system, the another one is a tie bar system. The current limiting reactor is inductive coil, large inductive reactance and compared with resistance. The main purpose of the inductance is to limit the short circuit current to the particular value during the fault condition. The current voltage reactors is also reduce voltage distribution on the rest of the systems. It is installed in feeders and ties in the generator leads and between the bus sections for reducing the magnitude of short circuit currents and effect of respective voltage disturbance. The current limiting reactor reduces the flow of short circuit current so as to protect the applicants from the mechanical stress and overheating. This is advantage of reactors. Current reactor reduces the magnitude of voltage distribution which caused by the short circuit current. To limit the fault current to a flow into the healthy feeders or part of the system, thereby avoiding the fault from spreading. This increases chances of continuity of the supply. This increases the chances of continuity of the supply. Main drawbacks of current limiting reactors are when the reactors is installed on the network, the total percentage reactor of the circuit is, this is the drawbacks of the reactors. It decreases the power factor and thus regulation becomes poorer. But main purpose of the reactor is to limit the short circuit current to a particular value and the chances of the increasing the continuity of the supply. The reactors located at different locations in a power system for reducing the short circuit current. The reactors are connected in series with the generator in the generator reactors, in series with the feeders or feeder reactors, in series with the bus bar is bus bar reactors. Generator reactors. Generator reactors are inserted between the generator and generator bus. Such reactor protect the machine individually. In power station generator, reactors are installed along with the generator. The magnitude of the reactor is approximately equal to 0.05 per unit. The main disadvantage of subtypes of reactors are that if the fault occurs any one of the feeder, the whole of the system will be adversely affected by it. This is nothing but generator reactors. The red color will be reactors. The first one is a generators and ABC are feeders. These reactors are connected in each generator, that is nothing but a generator reactors. Next, feeder reactors. The reactor which is connected in series with each feeder called feeder reactors. When the fault occurs on any feeder, then the voltage drop occurs only on its reactor and bus bar voltage is not affected much, hence the machine's continuity of the supply to the load. The other advantage is that fault occurs on a feeder will not affect the other feeders, thus effect of faults are localized. The continuity of supply will be increases. This is nothing but a feeder reactors. All the reactors are connected in series to each feeder, that is nothing but a feeder reactors. The third one is a bus bar reactors. When the reactors are placed in bus bar system, that is nothing but a bus bar reactor. When the reactors are inserted in the bus bar, it is called as a bus bar reactors. A constant losses in the reactor is avoided by inserting the reactors in the bus bars. In this system, only small power flows through the reactors during normal condition. During the short circuit on the feeders, only one of the generator feeder, the fault is directly bypassing the reactors. Sometimes the bus bars are sanctionalized and the reactors are included only between the sections of bus bars. This is nothing but a ring system, bus bar reactors. When the reactor and the bus bar is divided into number of sections and these sections are joined by using the reactors, this is nothing but a bus bar reactor. In bus bar reactor, this is a ring system. And tie bar reactors. And the reactors is divided into two sections and each of the reactor is half of the reactor that can be used in the bus bar system. The only disadvantage of the tie bar system is it requires two bus bars, that is nothing but another bus bar is nothing but a tie bar system. In case of tie bar system, the reactance of the reactor is nothing but half of the reactance that can be used in the ring system. These are the different types of reactors. Steps for symmetrical calculation. How to calculate the fault current or short circuit current. First draw the single line diagram. There are different steps for calculation of short circuit current and short circuit kVA. These steps are followed, then we simply to calculate the problems very easily. First, given power system, draw the single line diagram of complete network and indicating the ratings, voltage and percentage reactance of each element on the network. That is the first given single line diagram. We draw the single line diagram. In case of after drawing the single line diagram, the ratings of all the components are measured in the single line diagram. Next, choose the convenient convenient base quantities. How to selection of base quantities? Voltage and current are selected as a 1.0 per unit, but base kVA is selected that the sum of the ratings of all the equipment or the largest unit of the equipment or any arbitrary value. Like that, we choose the convenient value of base kVA. Choose the numerical convenient value of base kVA and converted all percentage reactance to this base value. Corresponding to the single line diagram of the network, draw the reactance diagram showing that one phase of the system and a neutral indicating the percentage of reactance on the base kVA in the reactance diagram. The transformer is represented as the reactances in series. That is nothing but finally, they calculate the total percentage of reactance from generator neutral to the fault point, that is percentage of X, and calculate the flow current of given value of selected base kVA and operating voltage. For these two values, we calculate the current, kVA and voltage, normal system voltage, then calculate the current, that is nothing but I. Finally, the various short circuit calculations are short circuit current is equal to full load current into 100 divided by percentage reactance, and short circuit kVA is equal to base kVA into 100 divided by percentage reactance. These are some important steps for calculation of short circuit current. This is nothing but one examples. These are the example or problems for calculation of short circuit current and short circuit kVA calculations. These are the theory topic of first half of the first unit. That is nothing but a symmetrical, that is nothing but a short circuit current and short circuit kVA calculation, representation of the single line diagram and impedance diagram and reactance diagram, and different types of reactors that can be used in the power system analysis. Sir. Topic.